Hello everyone, this is Sumit Gegre and I welcome you to the presentation of a very interesting paper called the Google File System. So what exactly is the Google File System? It is nothing but a scalable distributed file system designed for very large distributed data intensive applications. It was developed by Google in the year 2003 with features like providing fault tolerance while also running on inexpensive commodity hardware and delivering high aggregate performance to a large number of clients. It was very important development during its time. This is a high level view of what a Google file system would look like. The cluster consists of thousands of commodity machines called chunk servers. These are expensive off the shelf servers, do not cost much and allow you to scale out very easily. Uh, in any given cluster of GFS, there can be hundreds or thousands of such commodity servers, and this cluster provides an interface for the clients to either read or write files. Now, before diving into how the Google file system actually works, we'll first go through some important assumptions that the paper makes. The first one is that failures are the norm. Now, this is an obvious because the system is made up of cheap servers, and we would expect some of them to always be offline due to some or the other reason. So the reason for failures can be anything like application bugs, operating system bugs, human errors, disk network power failure, etc. And due to this reason, the system must detect, tolerate, and also recover from such failures on a daily basis. Next is the file operation. So we can expect millions of files with each file being at least 100 MB to be stored on the Google file system. The writes that are made on the system are mostly sequential append-only writes and random writes. The system is not optimized for random writes. Reads are also mostly sequential, and client applications have to optimize for small arbitrary position reads that the client needs to make. Let's see what interface is provided by the system. So the files are organized hierarchically in directories and identified by path names. Uh, Google file system does not adopt the standard POSIX interface. Instead, they have implemented their own. Operations like create, delete, open, close, read, and write are supported. These are basic operations. In addition to that, there are two operations that are also provided. One is snapshot, which allows the client to create a copy of a file or a directory tree at very low cost. The second is record append, which allows multiple clients to append data to the same file concurrently. There is a guarantee made here that at least the very first append is guaranteed to be atomic. So now we'll see the architecture of the Google file system. Before we go to the architecture itself, we need to be familiar with the concept of chunks. So files are split into fixed size chunks, and each chunk is of 64 MB. This is a very important design choice, and we'll see why in the later slides. Each chunk is identified by 64-bit ID called a chunk handle. These chunks are stored on different chunk servers, and each chunk is replicated on multiple chunk servers. The default value for replication is 3, so each chunk will have at least 3 replicas, but this can be customized by the client. The next important point in the architecture is the single master. So this is again a very different design choice of having only one single master. And the objective of this choice is that it decouples the data flow from the control flow. So what does this single master node do? The master is responsible for all system-wide activities like chunk lease management, reclaim storage space, load balancing, etc. It also maintains all the system metadata like the namespace, access control information for different clients, the mapping from files to chunks, and the current location of the chunks. The master periodically communicates with each chunk server in heartbeat messages. This helps the chunk server in determining the chunk locations if at all they have changed, and also it helps it to determine the overall state of the system. Now, the most important point here is that all the metadata that is stored by the master is stored in memory. This is a pictorial representation of what goes on in a typical Google file system. So we have a single master. The master stores all the information related to a file in a table. We have the file name, the IDs of chunks in which the file is divided, and also the location of these chunks. So the control flow is between the master and the client, and the data flow is only between the client and the chunk servers. So both the control flow and data flow are separated from each other. Client is not riddled with all the data queries by the client. The chunk size and location. So we saw that the chunk size is 64 MB, and this is a key design parameter. This is because it provides the following advantages. So it reduces the client's need to interact with the master, because the client gets a lot of data in a single request. Also, since the client is likely to perform many operations on a given client, keeping a persistent TCP connection to the chunk server reduces the network's overhead. Also, it reduces the size of the metadata stored in the master. So as the size of the chunk increases, the number of chunks will decrease, and the data that the master has to store will also decrease. Master does not keep a persistent record of which chunk servers have a replica of a given chunk. Instead, it simply polls chunk servers for that information at the startup, and then periodically keeps updating this information. This implies that chunk server has the final word over what chunks it does or does not have on its own disks, and not the master. Uh, Now, the important question here is, why was this design choice made of storing metadata in memory? So, speed is the obvious advantage here, because you have all the data readily available. Furthermore, it is easy and efficient for the master to periodically scan through its entire state in the background. Also, uh, this could be a potential concern for many, because we are being limited by the master's memory to increase the system capacity. But in practice, this is not a limitation, because all that master maintains is a 64 byte metadata for each 64 MB of chunk, and most chunks are full because we have large files stored. And hence, if necessary to support even large file systems, the cost of adding extra memory to the master is a small price to pay for the simplicity, reliability, performance, and flexibility we gain by storing the metadata in memory. So one of the important concepts when it comes to the reliability of the system is the operation log. So it is nothing but a central log containing the historical record of critical metadata changes that have happened on the master. It is the only persistent record of this metadata, and it also serves as a logical timeline that defines the order of the concurrent operations that have been happening. This operation log is replicated on multiple remote machines. The use of the operation log is when the master crashes. So to minimize the startup time after a crash, the logs are kept very small in size. And to do this, the master checkpoints its state whenever the operation log grows beyond a certain limit, so that whenever a master goes down, it can recover very fast by loading the latest checkpoint, and only replaying the limited number of logs that have been stored in the operation log. Uh, Now, this design choice of having a single master, what are the benefits of this? So the most important benefit is simplicity, because master has the global knowledge of the entire system, and that drastically simplifies the design, solves a lot of problems for the developers. Also, master has minimal participation in reads and writes, which ensures that it never becomes a bottleneck. So because the data flow is only between the client applications and the chunk servers, the master never participates in those, and it will hopefully never be a bottleneck. The clients only request from master which chunk servers they have to talk to, and furthermore, to reduce the load on the master, clients also cache this information for a limited time, and once they have the cache, they can directly interact with the chunk servers without having to talk to the master. Now we'll see how a typical read happens in the Google file system. So the first thing what happens is that the client asks for the file name or the chunk index to the GFS master. So if it is reading the file for the first time, the client will ask for the will query with the file name, or if it is already in the middle of reading a file, it will query with the chunk index. The master returns the chunk handle and all the chunk locations of the file. So by chunk locations, I mean the different replicas that are stored on different chunk servers. And the once the client receives this, with this information, it can query the chunk servers um, to receive the data related to that file. Uh, Next, we'll see the writes, but before going into the writes, we need to be familiar with leases and mutation order. So mutation in the paper is defined as a change in either the metadata or the contents of a chunk. So each mutation is performed at all chunk replicas, and a consistent mutation order is maintained using leases. So what is a lease? Master grants a lease to one of the replicas, and this replica is called primary. So whichever chunk holds the lease is called the primary. The primary then picks a serial order for all the mutations to the chunk. So master will grant a lease to a chunk which is called primary. Primary, we select a serial order in which all the replicas will update the information. So this minimizes the management overhead at the master because it is being done by the chunk at the chunk servers. The lease timeout is 60 seconds, so the primary will lose the lease after 60 seconds. But in case the mutation takes longer, the primary can request an extension for the lease. Let's see how a typical write happens. So first step is that client will ask for the master for an empty location. So any chunk server that the client can store the file to. Master will send the IDs of the primary and secondary replicas at which the client can store the chunks. Next, client will write the data to all these replicas. Now it is at this stage the data has only been written and not committed. Then it will request commit to the primary. The primary will commit the written data, and then the primary orders writes to the secondaries, and this is done in a serial order that is decided by the primary replica. Once the secondaries have committed the data, they acknowledge the primary, and primary in turn acknowledges the client about the successful write of the data. So here we can see that this is the control flow and data flow, and the control flow is only between the masters, and the data flow is only between the chunk servers. Now let's see the data flow. So data is pushed linear. So this data flow is within the chunk servers through different replicas. So data is pushed linearly along a chain of chunk servers. The goal is to fully utilize each machine's bandwidth. Each machine transfers data to the closest machine in the network. Latency is minimized by pipelining transfer over TCP connections. So once a chunk server has received some data, it immediately starts forwarding it. It does not wait to complete that transfer and then again start receiving some other data. So overall, this we can say that the chunk servers are connected in a chain, and there's no tree or star topology that is being followed here. Let's see what the replica placement policy is. So how does the chunk replica placement policy protect against network partitions? The GFS cluster is highly distributed, and we know that there are hundreds or even thousands of chunk servers that are spread across many different racks. Now, the communication between multiple racks may cross one or more network switches, and here comes in partitions. So the replica placement policy solves this problem by multi-level data distribution. It maximizes data reliability, and it also maximizes network bandwidth. So replicas are spread across racks. Replicas are not just stored on different servers in the same rack. They are also stored. The replica placement policy makes sure that the replicas are stored on the servers in different racks too. This ensures that some replicas survive even if an entire rack goes offline. So reads can exploit this placement policy can also be exploited by reads because the aggregate bandwidth of multiple racks will increase. And the trade-off that we are making here is that the writes traffic has to flow through multiple racks. So the writes might be slow. Next, we'll see garbage collection. So how does GFS do garbage collection? So GFS follows lazy garbage collection. What does lazy garbage collection? So once a file has been deleted, that is, it does not exist on the chunk servers, the available storage is not immediately reclaimed. So the file is renamed to a hidden name, which includes the deletion timestamp, and such files are deleted during regular scans if they exist, if they have existed for more than 3 days in the system. So until then, the file can be read and it can also be recovered. So after the hidden file is deleted, its metadata is also deleted from the master. So in regular scans, master identifies. Now this was for the reclaiming storage, but what about the chunks? So in regular scans, master also identifies orphan chunks. Orphan chunks are those which the master does not know about, and erases metadata for those chunks. It also lets the chunk servers know which chunks are not present in its metadata, and then chunk servers is free to delete its replicas for such chunks. So it lets this communication happens in the heartbeat messages. So during the heartbeat message, master can let the chunk server know that such which chunks are orphaned, and then chunk server will delete its replicas of such chunks. Now, what are the advantages of this garbage collection, lazy garbage collection? Now let's see what would be the advantages of this lazy garbage collection. So the first is that it is simple and reliable in such a large scale distributed system where failures are the norm. Also, it is a uniform and dependable way to clean up any useless replicas. Garbage collection is merged with the regular background task, hence the cost is amortized. So because the master does the garbage collection in the regular scans, the cost is amortized. Also, this is done when the master is relatively free, because really the regular scans are done when the master is not being is not a hotspot in the peak hours. Uh, Also, delay in storage reclamation provides a safety net against accidental and irreversible deletion. So this, we do not want to lose data which the client needs to keep safe. So this also helps us in avoiding that. So next, we'll see the fault tolerance in GFS. So this is also an answer to how the GFS provides reliability. So first is fast recovery. Master and chunk server. We have seen this because master and chunk servers restore state and start in seconds regardless of normal or abnormal termination. In fact, the developers at Google do not have a turn off mechanism, a shutdown mechanism. They just switch off the entire system. So the system is fault tolerant enough to recover easily from such terminations. Also, we have seen chunk replication. So chunk replications improve the reliability of the system. Also, we have the master replication. So how is the system reliable if we have only a single master, and how does the system handle if that single master goes down? So the master state is also replicated for reliability on multiple machines using the operation log and checkpoints. So clients use only the canonical name of the master. So this is an example of what the clients would identify the master with, and this is a DNS alias that can easily be changed if the master is relocated to another machine. There's also a concept of shadow masters. So shadow masters provide read-only access to the file system even when the primary master is down. So they read a replica of so shadow master is nothing but a copy of the master. They are only a few seconds behind the actual master, and when the master goes down, they can still provide read-only access. They read a replica of the operation log and apply the same sequence of changes to them. So they are not mirrors of the master, they just lag the primary master by fractions of seconds. This means that we can still read up-to-date file contents while master is in recovery. So to conclude, GFS can be used to store huge amounts of data while catering to large number of clients, which is difficult to achieve with vertical scaling. Also, the key part of this paper is decoupling of data flow and control flow by having a single master and storing the data on chunk servers. As the files are distributed across machines, it helps in performing batch processing much faster than a traditional server. MapReduce utilizes this, and MapReduce together with GFS is very efficient. GFS also not only served Google storage need when it came out, it also formed the basis for the Hadoop file system. So it would be very interesting to see how the Hadoop file system was designed to be administrated and set up for any application while taking GFS as a basis for its development. So this is all about the Google file system. Thank you for your time, everyone.